Thanks everyone for tuning in to my presentation today. I just wanted this to be a very short 10-minute interim update about what I've been working on, which is exploring relative navigation techniques using a fusion of differential GNSS with optical and range aiding. It is incomplete work in progress, and so today I only am able to share my methodology, but I aim to have a set of presentable results by next quarter. So I'm sure most of us are familiar with the value proposition of formation flying spacecraft, and so I don't have to talk about this in detail, but what's really exciting is that VISERS, the upcoming mission that SLAP was in charge of the GNC for, will be testing onboard integer ambiguity resolution with differential GNSS. So let me just go to what the current challenges are. A critical requirement that actually ensures the success of any formation flying mission is accurate relative state knowledge of all actors within the vicinity of a formation. And this includes state knowledge of cooperative actors as well as uncooperative actors. Knowing precise knowledge about our states of our cooperative actors allow for controllability of the formation baseline that will enable our science mission. Knowing the precise relative states of uncooperative actors allow the formation to plan for the risks of in-orbit collisions, or conversely, to plan for a deliberate rendezvous to the said uncooperative actor. So in the scope of this presentation, cooperativity is defined with respect to a chief spacecraft by whether an agent can establish an intersatellite link and respond to it accordingly. So on a very high level review, here are 3 common techniques that SLAP has a lot of experience in relative spacecraft navigation. So first, monocular angles only navigation, which has been tested on Prisma, BIROS, and in future Starlink, allow for the exploitation of ubiquitous optical sensors such as cameras and star trackers. The advantages are that the non-range ROEs are strongly observable. However, the homothetic range ambiguities make the range ROE state, or equivalently the relative mean longitude of, the relative mean longitude weakly observable. Previous work by Justin and Joshua on Artemis have proven that the range can still be recovered over long arc observations by exploiting non-linearities in the dynamics, as well as periodic variations in the elevation angles of the target spacecraft. However, in time-critical operations, proximity operations, this may not be too desirable. A second technique, stereo vision, is another option that SLAP has strong experience in, particularly for SNAC in the ANS project. Like monocular vision, the sensors are common and simple for spacecraft, and the range ambiguity this time can be resolved rapidly. However, it comes with the complexity of coordinating multiple cooperative observers, sharing individual angles-only measurements across the entire swarm with respect to a target that could be both cooperative or uncooperative. The third would be differential GNSS, which is a primary mode of state estimation in digital. And this exploits powerful error-canceling techniques between shared carrier phase measurements of cooperative-only spacecraft. Digital attempts to estimate what is known as the integer ambiguity in the difference carrier phase measurements. And this is known as IAR, or integer ambiguity resolution. For some of us who are not familiar with the term IAR, I will also give a brief 3-minute explanation about it shortly. One shortcoming of solely using differential GNSS is its vulnerabilities to unmodeled environmental noise, such as ionospheric scintillations arising from solar storms and geomagnetic activity. The other possible technical noise source could be from the space and ground segment of the GNSS constellations. These noise sources are beyond the control of our hardware and may result in a bad integer ambiguity fix, possibly causing filter divergence, and it will jeopardize on-orbit operations. So the long-term research idea that I have is to combine these measurements into a single unifying framework that allows a spacecraft formation to maintain a situational awareness map of both cooperative and uncooperative resident actors at far range. And by far range, I mean that the targets appear as points, or equivalently, the rigid body features are not discernible within the camera itself. For cooperative and communicable targets that have mutual access to GNSS and angular measurements of each other, the hypothesis is that the bearing angles can set a constraint on the double difference integer ambiguities to aid the IAR search process. Again, if you're not familiar with the term double differencing, I will talk about it shortly. This will narrow the search towards a correct integer fix even under heavy presence of unmodeled noise. The shared bearing angles can also be used to perform state estimation of uncooperative targets via stereo vision. For non-cooperative targets, the hypothesis is that the precise baseline knowledge between observers that we can get from digital, as well as the rotational information from the spacecraft ADCS, enables triangulation of uncooperative targets with at least 2 observers in the formation. Information from digital would be, as well as the ADCS, would be sufficient to establish the essential camera matrix, which is given by this line here, if using 3D coordinates, or the fundamental camera matrix if we're using the image coordinates as seen in the last equation over here. The goal is to create a dynamic baseline stereo system that can circumvent the homothetic range ambiguity problem faced in monocular angles only navigation. However, settling down on a more realistic short-term goal, I will focus on first improving the precise relative navigation baseline between cooperative observers by employing digital with its state-of-the-art IAR techniques and constraining the integer search process using angles and range measurements, with possible applications to visors as well as future lunar navigation missions, which I think is a buzz topic that I want to base my literature review on as well. For the benefit of us who are not familiar with differential GNSS, here's a quick 2-minute walkthrough. So consider that the carrier phase model between a transmitting GNSS satellite and a receiver, the phase is modeled by the true range, which is R over here, between the receiver and the transmitter, offset by the number of integer wavelengths, and corrupted by ionospheric delays, receiver clock errors, and the transmitter or GPS satellite clock errors, as well as relativistic effects, as well as other error terms. When the carrier phase measurements of 2 spacecraft, A and B, are communicated to each other and differenced, the common error terms such as the ionospheric delay, the symbol I over here, GPS clock errors, as well as relativistic effects actually cancel out. So everything in the red boxes cancel out, and this leaves us with a measurement known as a single difference carrier phase. Geometrically, if we consider that the direction of arrival of the GPS signal reaches both spacecraft almost parallel by virtue of the far field approximation, then the single difference true range forms the baseline of a right-angled triangle with the baseline of interest as the hypotenuse of this triangle. Assuming we have an estimate of single difference receiver clock biases, delta TAB over here, as well as the single difference ambiguities, then we, with 4 single difference measurements, we may solve via least squares the baseline solution of our spacecraft. And so now consider that if we take the difference of 2 single difference measurements across 2 GPS satellites, where 1 GPS satellite serves as a reference, this will be known as double differencing. The nuisance single difference receiver clock bias is common to both measurements, as seen in this equations when you difference both single difference measurements here, and so they cancel out, leaving behind the double difference true range as well as the double difference integer ambiguities. And geometrically, just like the single difference, we can form a set of linear equations for the double difference measurements and resolve for the baselines using a relative geometry matrix, which is the difference between this direction vector and this direction vector here. So once we do the double differencing, notice that we are left with the double difference integer ambiguity term, which is this symbol NAB, where AB represents the spacecraft and PQ represents the two GPS satellites that we're taking differences with respect from. And then we move to how we're going to resolve these integers. So integer ambiguity resolution is the art of finding out what N subscript AB, superscript with the GPS satellites PQ, what this value is. The state-of-the-art has remained the dominant technique for 28 years and is known as Lambda, the least squares ambiguity decorrelation adjustment. In summary, due to the integer nature of the ambiguities, a discrete search for the integers must be performed. As double difference measurements are highly correlated due to the choice of a common single difference reference, Lambda reduces the size of this search space by decorrelating the ambiguities using a coordinate transform known as a Z-transform. This preserves the integer nature of the ambiguities. The covariances are decomposed using an LDL decomposition, and the transform ambiguities in digital are rearranged such that ambiguities with the lowest decorrelated variances will be processed first. Doing so allows us to attain an initial guess much more quickly via integer bootstrapping, which is a simple rounding of the very first ambiguity, which we arranged to have the lowest variance. And then for ambiguities thereafter, a sequential recursive conditional rounding is performed using the integer bootstrap formula as seen in this box over here. The search is then performed in Z-transform space. So notice what happens after the decorrelation is that instead of a long ellipsoidal search width, I now have a decorrelated space where my search width has condensed into somewhat close to a spheroid shape. Once the integers are searched within this domain, it gets resolved back into the real integer space and then resolved back as from a double difference ambiguity to a single difference ambiguity. So that's the summary of vanilla flavored differential GNSS with integer ambiguity resolution. And so I'm going to share with you the methodologies and changes I've made to digital to include azimuth, elevation, and ranging. So this is the original digital. This is just a filter block of digital. The time update is an absolute orbit propagation with a geopotential 20 by 20, and it doesn't directly update the states. What the orbit propagation does is it updates coefficients of a fifth-order Hermite polynomial fitted to the states. This allows for on-demand precise relative state estimation using polynomial interpolation, which is a lot less computationally expensive than performing frequent high-fidelity orbit propagations. As explained before, for the measurement update, digital uses these powerful error-canceling differential techniques to perform the measurement update of the filter's relative states, as well as to estimate the float ambiguities in single difference form. IAR is then used for data editing of the ambiguities after a fix, and the improvements in accuracy will be reflected in filter measurement updates in future epochs. The first option for data fusion with digital is what I term a loose coupling. Simply put, a linearized update of the states using the measurement model is performed. In implementation, this is simply two functions, a laser range update, as shown in this box, and a camera or angles only measurement update. The key highlight between the implementation detail of these two functions is that they must be able to be called asynchronously with the GNSS data measurement updates, as the time tags between the GNSS data and the time tags of the laser ranges and the time tags of the camera angle measurements may not be synchronous. The second option for data fusion includes both the measurement updates as well as allowing external AER measurements or azimuth elevation range measurements to constrain the IAR process. An alternative optimizer was devised where it keeps track of not just the ambiguities in that epoch, but all double difference ambiguities fixed for all epochs as long as that GNSS pseudo-range number is observed. Like Lambda, it uses the initial integer bootstrap as the initial guess in Z-transform space, and then it performs a constrained search before fishing out an ambiguity value and resolving it back to the tracked single difference ambiguity. I'll talk more about how this new constrained search is implemented in the next slide. From the earlier slide about the geometrical interpretation of double difference measurements, with sufficient measurements, we can set up linear equations as follows. The superscript over here, in these measurements, where there's 1L to K of L, they represent the two GNSS satellites that are used to extract double difference measurements, where L is the reference. The double difference geometry matrix, which is this giant block here, is summarized as the symbol G in the linear equations below. And lambda is the signal wavelength in the carrier phase measurements. And it refers to double difference ambiguities. And once we have sufficient number of these double difference measurements, we can estimate the baselines X tilde and N tilde. So N tilde is the float ambiguities. I use tilde as a notation for the estimated states rather than the true states. In digital, these measurement updates are done sequentially in the Kalman filter rather than presented in this way as a batch least squares form. So using the float ambiguities, an initial rounding using integer bootstraps is applied. So since the probability of fixed via bootstrapping provides a lower bound to the probability of fixed via integer least squares, we use the float ambiguities and the bootstrap integers to set a search width automatically using the metric that was devised by Tunison in 1994. Once we have the search space defined, we can begin the search process. During the search, for every unfixed integer candidate, we perform a Z transform on the estimated float and on the double difference covariance matrix. From the vanilla flavored lambda, the cost function is only a single quadratic cost expressed in the Z domain rather than the real integer domain. Using the double difference carrier phase measurements, we construct a candidate baseline solution for each candidate set of integer ambiguities in the search space. This candidate baseline solution is then transformed into the camera frame or the vision sensor frame, and the azimuths, elevations, and ranges will be computed using these candidate solutions. The cost function then takes in the difference between the observed azimuth, elevation, and range measurements from the sensor, and the computed azimuth, elevation, and range values from the candidate solution. This cost function is then normalized over the baseline magnitude squared and scaled by the wavelength squared so that the units commensurate with the dimensionless integer ambiguities. The cost function of the observed minus computed azimuth, elevation, and range is then added to the cost function of the integer search. The best two candidates will then be saved and run through Lambda's probability of successful fixed test as well as the discriminator test. At this point, I do not have a complete set of results as I'm still in the middle of toying with the optimizers. Gradient-based optimizers are not really feasible due to the integer constraint, so search-based optimizers are being tried as per the original Lambda. During many failed experiments, the biggest cause of failure is usually the acceptance of a bad fix, which causes filter divergence towards the point of no return. And so a critical gap that I have to address in this research is to devise not only a methodology, but also a safeguard against bad data editing moving forward. I aim to have a good set of results, hopefully by next quarter, and I look forward to sharing it with the rest of the lab. Thank you.